Okay. I once again welcome you all of you the lecture series of microprocessors and microcontrollers. Now today we are going to discuss the ADC interfacing to the 8255 PPI. So ADC means analog to digital converters. Nothing but analog to digital converters. How these converters are interfaced to connect the 8255 PPA. Okay. So this is very much essential that so whenever you want to connect 8255 PPA to the 8086 microprocessor, so at the same time you are also interface this some any input output devices to this 8255 PPA like analog to digital converter, so digital to analog converter, some keyboard as well as some monitors as well as some printers, some scanners, those are the devices to interface the 8255 PP. Now, today's class we are going to discuss the analog to digital converters, that nothing but the ADC. Okay. Now see this. Now see this ADC. Now see this ADC, analog to digital converters. These ADCs are available in 8-bit as well as the 12 bits. So these ADCs are nothing but the analog to digital converters are available in 8-bit as well as the 12 bits. So you know that these are analog to digital converters, nothing but for suppose I given it as a sine wave. For suppose this is sinusoidal wave as a voltage or current. This is time. This is t. Voltage is current. So this may be convert into the 1001 format. 10 is nothing but the 1001 format. Convert to the digital. This is analog format. This is analog format to the digital is nothing 1001 format. Is okay. It's converted into the 1001 format, like digital format. So for that purpose, you require the analog to digital converter. So these are the input devices. Input devices to the microprocessor. These are the input devices to the microprocessor. So when you operate this analog to digital converters, this analog to digital converters has two main signals. This ADCs has two main signals. One is SOC, start of conversion, and second one is end of conversion. Start of conversion and second one is end of conversion. So what is the meaning of start of conversion? Whenever our microprocessor is initiated by start of conversion, is nothing but so this ADC is converting analog signal to the digital signal. Once this process is done, so whenever it converts some analog to the digital, it takes some time. So after some time, this ADC generates the EOC. EOC is nothing but end of conversion. So I am converting the signal from analog to the digital. This time you can call it as a or conversion time. The total conversion time you can call it as a conversion delay or delay time. Conversion delay or delay time of an analog to digital converter circuit. Okay, there are two types of conversion technique. This analog to digital conversion technique, there are two types. First one is successive approximation method and second one is dual slope integration method. Okay, what are the two methods? First one is successive approximation methods as well as dual slope integration methods. These are the two different conversion techniques. Okay, so what is the conversion delay or delay time? The time required to convert an analog signal to the digital signal is called the conversion time or delay time. One thing you should remember in this conversion time as well as delay time, whenever the signal is converting the process. So the input of the signal, what is the input signal to this device ADC? What is the input signal is nothing but what is the signal? Analog signal is constant. Otherwise it is not going to convert the exact signal. So constant. So until the conversion time is over, up to that, the signal, analog signal is constant. For that purpose, we require this some sampling, holding or sample or holding circuit. So whatever may be the techniques you are using for converting some analog to the digital, nothing but there may be a successive approximation or dual slope integration methods. So there is some general algorithm for this one. So what is this? The first point for writing the algorithm is ensure the stability of analog input applied to the ADC. Stability of analog input. Stability means in the conversion process up to the AOC to the EOC, start of conversion to the end of conversion, the signal, the analog signal is stable, nothing but constant. For that purpose, you use the hold and the sampling device or circuit. Otherwise, for suppose this is a sinusoidal signal for converting analog to some digital, some 0 1 1 0 format. If the signal is varies, so we will not get the exact output for this microprocessor. You can analyze the any signal. So what is the if there is any errors in that signal, there is a fault analysis or whatever it may be, you can analyze that signal. What is the amplitude of that signal? What is the magnitude of that signal? So what is the voltage levels of that signal? What is the current levels of that signal? Whatever it may be, analyze any signals. So that signal is constant for entire conversion delay time. That may be of 3 microseconds or 2 milliseconds or nothing, but that is the time for converting analog to the digital. So on that time or 2 or 3 microseconds on that time, the signal, the input signal is constant. So that is the first one. What is the second one? So it can start the start of conversion and end of conversion. Both in a successive approximation method as well as dual slope integration method, you use the start of conversion and as well as the end of conversion. Again, what is the fourth point is read digital data output of ADC equivalent to the digital output. So this is the some central algorithm for converting some ADC to the some analog to the digital conversion. Now see this. So you can go for the what are the different types of ADCs available to interface the 8255 PPI. Now see this. We have now we are going to discuss here two different ADCs. So ADC 0808 or 0809 8-bit converter. This in this conversion technique you can use it as a successive approximation. Successive approximation. So what is the another type? Then second one is the ADC ICL 7109. It is a 12-bit converter. This we can use it as a dual slope technique. Used it as a dual slope technique. So here two types of analog digital converters are available. First one is 0808 or 0809 8-bit converter is available. At the same time, ADC ICS intersil. ICL means intersills 7109 a 12-bit converter is available. So in this 8-bit converter, they can use the successive approximation method for converting an analog signal to the digital signal. So in this ADC 7109 at 12-bit converter, they can use the dual slope technique to convert an analog signal to the digital converter as signals. Okay, now going to discuss the ADC 0808. So what is the basic structure of this ADC? Simply see this ADCs and how to interface that one. So see this, this is the 8086 microprocessor. Okay, this is the 8086 microprocessor. So in this microprocessor, we are going to interface the 8255 PPI. In this 8255 PPI, we are going to add an input device. The arrow is series, an input device of See this arrow. This is dual way. This is only one way. That this is the port A or B, whatever. This is ADC. So this is the basic structure to interface the this ADC, any of the ADC to this microprocessor. Between that, we have the 8255. Okay, our main discussion is lies in how this ADC is interfaced to this 8255 PPI. Okay. Okay, I think we are already seen how to interface the. We are already discussed the how to interface 8255 PPI to the 8086 microprocessor. We are already done that. But now we can see the how these ADCs are interfaced to this 8255 PPI. Okay, so for this interfacing this ADC to this 8255 PPI, you can use the port A, port B, or port C also. And 8-bit. This is the 8-bit. This is the 8-bit for suppose 8-bit or 12. Whenever you are using 12-bit, in this case, you can combine uh, port A or port B. Combine port A or port B in the 12-bit case only. Otherwise, you can directly connect the an ADC to this 8255 PPI. You can see this is an input device. An input device. Nothing but this analog. So this ADC you are giving some this ADC input you are giving some, for suppose I can connect the some source like some sine sinusoidal generator, sinusoidal generator, or any generator output, or generator output. Our aim is for this analog signal or sinusoidal or triangular, whatever it may be, triangular signal, or not only the sinusoidal, that may be of any of the analog signal, any of the analog signal. This is also one analog signal. DC is also the analog signal. Any of the analog signal you are using. This analog signal we are going to analyze the analyze what are the analyzing components, what is the voltage level, what is the current level, any fault level is there in the microprocessor, what is the frequency levels, and etc. Nothing. So for that purpose, this type of inputs we are giving this ADC. What is this ADC? This ADC is converting this type of signal to this 1001 and giving this signal to the 8255 PPI. So nothing but this to the 8255 PPI. Then 8255 PPI is given to the 8086 microprocessor. This is the process. Okay, you understand the process? So this is the process. Okay. Now see what is this ADC? What is this 808? 8088 is 88. How that is built, and now you can see it. Now see this. This ADC 08 or 09 is a 12-bit. You know that 12-bit successive approximation converter. We are using the technique called successive approximation to convert. So what is the conversion delay? You can assume that the conversion delay is 100 microseconds. 100 microseconds. And that of clock frequency is 640 kilohertz. These are some assumptions. Okay. For this converter, for ADC, we are using 3:8 ADC. 3:8 ADC. 3:8. So we have three input lines. So three input lines. ADD, nothing but EAD, address A, address A, address B, address C. You have three input lines. Now you can give it to the 8 output lines. Eight output lines. Output lines 8. Why 8 output lines? This is the 8-bit converter. This is the 8-bit converter. So 8 bits. 8 output lines. It's nothing but the 8 bits. One line is indicates the 1 bit. So 3:8. So we are giving 3 input signals, giving 3 parameters of that input signal. We convert 8-bit of that converter. So for these lines, we are using the conversion of the lines. So 3 lines. So these are the 3 address lines, and inputs multi-channel data acquisition system can be designed using this ADC. Okay, now see this how this ADC is. So this is see this some address lines for suppose. So see this these are the Analog input selected IP0, IP1, IP2, IP3, IP4, IP5. Now three is understands ABC. This is 0, this is 1, this is 2, this is 3, this is 4, this is 5, this is 6, this is 7. You know that you have eight address lines, 8 lines. So 3 is to 8. 3 is to 8 is nothing but the three inputs, three address lines A, B, C. Then what are the 8 lines? IP0 to the 8. IP0 to the 8. See this. In the three combinations, you write these 8-bit numbers. 0, 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, something like that, 8. Nothing 0 to 7 is nothing but the 8 lines. So it's nothing but the 8. 8 lines are bits. So by using this three address lines, ADC. Now see this. This is the black diagram of ADC. So see this. So what we are discussing is ADC. Now see this IP0, IP1, IP2, IP3, IP4, IP5, IP6, IP7. Again 8 bits, 8 lines are 8 bits. Okay. See this this is a 3 is to 8. See this 8 channel analog multiplexer, 3 is to 8 multiplexer. So now see this, we have the SOC. You know the what is the meaning of SOC? You know that what is meaning of SOC? Start of conversion. Start of conversion. What is EOC? End of conversion. Who can initiate the start of conversion? Who can initiate the start of conversion? And microprocessor is initiating the start of conversion. And microprocessor is initiating this startup conversion. So microprocessor is not directly initiating the startup conversion. In between this microprocessor and this ADC, we have what is that? At 8255 PPI. So the microprocessor is send some commands to this 8255 PPI. This 8255 PPI is send the instruction to start the conversion, nothing but analog conversion. That may be a first star or triangle signal or whatever, some signal. So once this ADC is converting that signal, you can send the signal to the 8255 PPI to the conversion is end. So in between the start of conversion and end of conversion, it takes some time to convert. That time we can assume it as 100 microseconds. 100 microseconds. This we can call it as a conversion delay or delay time. Conversion delay or delay time. So these are the 8 outputs. So these output lines are connected to the 8255 PPI. This output lines, this 8-bit output is connected to the 8-bit port of PA027 or PB027 ports. PA027 or PB027 ports. So now this is connected to the 8086 microprocessor. So this is the basic structure of the black diagram of 0808 or 080. So this is the output latch. This is the an output latch. So this output latch, you know that. This has the 8-bit. This is 3 is to 8. So 3 address lines and 3 input lines. 3 is to 8 converter and ADC. Okay. Now see this how this ADC is interfacing this 8255 PPI. See this. So this is a basic pin diagram of this is 28 pins. 28 pins. ADC. 28 pins. Now we can see the some simplified version of the this pin diagram. See the simplified version. What are the input lines for this one? What are the input lines? IP0 to the 7 input lines. So what are the again the input lines? What are the again the input lines? So what are the other input lines? ADD A to the C input lines. Okay. Again, you have the so you can see this 7 and 8 and the 3. Okay, 11 lines are over. Then we have the some output lines also. What are the output lines? Output lines. O0 to the 7 are output lines. OP O0 to the 7. How many lines are over here? Out of 28 pins, how many pins are completed? So 8, 8, 16 and 3, 19 lines are over. Remaining lines are 9 lines. You can see the what are that remaining lines. So one is you know that one is SOC, another one is EOC, end of conversion, start of conversion. Then one line is dedicated for the clock. Then one line is VCC, you know, the power supply, and then is the ground. No series. So I think almost all total pins are so 19, 20, 21, 22, 23, then 24 pins is over. Then we have the some lines for ALE, address latch enable lines is available. Okay, then output enable OE lines. One line is OE line. Okay, then we reference plus here. We reference plus is here. We reference minus is here. So 19, 20, 21, 22, 23, 24, 25, 26, 27. One line is missing, I think. Yes. Yes, ground line. It's 28 pins are available. You see, it's very easy. So out of this, 19 pins are dedicated to the input 0 to the 7, output 0 to the 7, then A, D, D, A to C. So 19 pins. Remaining 9 pins are 2 for V reference, then ground, VCC, ALE, SOC, then EOC. This is the way to remember the pins. So whatever we are using here, see this EOC clock, SOC clock, EOC, then input lines, then output lines, V reference plus, V reference minus. Okay, output lines, output enable, OE, output enable, OE lines. So 8-bit port. This is output 8-bit ports. The same lines we are drawn here. Okay, so remember this one. I draw in our notes. This is the simplified diagram of this ADC 08 08 or 0809. Okay. Now see this. You know that these are the analog input ports. The analog input. You know this. These are the 8 lines. 3:8. Then output. These are the output lines. Output 0 to the 7 lines. So SOC start of conversion, end of conversion, output enable. This is the output enable, clock, VCC and ground. So the power supply are given it is the 5 volts and ground. Then V reference and V place. So V reference means here, so 5 volts maximum. You take the 5 volts maximum voltage and V reference negative is 0. So 0 to the 5 volts to the 0. So reference voltage. Okay. Now see this. How to interface ADC to the 8255P. Okay, so now see this, they can ask the problem in the examinations also, they can ask like this, and otherwise they can straightly ask that. So interface 0808 to the 8255P. Okay, so first of all they can ask the problem is like ADC 0808 with 8086 using 8255P using port A. You see this, using port A. So this is the important part. Using port A. If port B is taken, so there is some. So all are same. The only changes in the program. So we are you write the program to interface this ADC to the 8086 microprocessor. So the only change is the program. So only one command is changing. Remaining all are same. I will tell you one or two commands are changed. So I will tell you what are the commands. Okay, see this. So to transfer the data ADC, so by using control signals, what are. So see this, the timing diagram of this one. So you know that this is a clock diagram. This is the clock. So for this one, ALE or start, you can consider the start of conversion or end of conversion, start of conversion, SOC. So for the first clock time pit 1, T2, T3, T4, T5, T1, T2. Once this SOC or AL is initiated, so on the time, for suppose you can assume You can assume the signal is late. Up to the completion of this EOC, end of conversion, this is the starting point. So up to the completion of this EOC, the signal is constant. The signal, whatever the given input signal, that is constant up to the this falling edge, this falling edge, this ending edge. Okay, up to this is constant, then only it will convert 10015. This is to the this. Otherwise, the input is changing, output is constantly changing, so we will not get the exact output results. So once OE output enabled, so this will be given into the latch. Once it is enabled in this one, so the data EOC conversion data is loaded into the output lines of ADC output lines. Yes, this is the data. This data is connected to the 8255 PPI. Once you can OE output enabled, you can give this output and whatever the data of that ADC is loaded into the 8255 PPI. So nothing but the output lines of that ADC. So this data is connected to the 8255. This is the some timing diagram. Very easy. So now see this interfacing ADC to 8255 PPI. So now this is the interfacing diagram. Interfacing 8008 with the 8086 microprocessor with the 8255 in this side. In the examination also we draw this. This is mandate. This is 8086 microprocessor. 8086 microprocessor. So this is 8255. So they can given interfacing 08 with 8086 microprocessor. They can given the name is here, but they can miss this microprocessor. This is the microprocessor. This is the 8255 PPI. This is ADC 0808. Okay. So in the examination you must draw this one. Simply you just draw like this. 8086 microprocessor just connect in this line. So in the microprocessor side, you can connect this 825 PPI. You know that very well. These are constant. You are not changing. These are read and write control logic lines. These are read and write control logic lines. You know that. So this part is already done here. Just you are concentrating this one to the, so this one to the this one. You are concentration this one to the this one. Okay. Okay. You are, because this part to the this part you are already completed. In the interfacing 825 PPI to the 8086 microprocessor. Nothing but this line is fixed here. This A to A1 lines, reset lines, read and write control lines. These are the read and write control logic of this lines given it to the 825 PPI. In this we have the CWR also. So by using this CWR, you can operate this 825 PPI in different modes. Nothing but mode 0 or simple input output mode, but mode 1 stored input output mode, mode 2 stored bidirectional IO mode, or BSR mode can operate it by using this read and write control logic, nothing but A0, A1, RD bar and other lines. Okay, so our intention is to how to interface this ADC to this 825. You know that ADC, what are the some signals of that ADC? So reference V positive, V negative, V positive, E negative signals. So 5 volts VCC. You know that what are the signals that is available in this series. As you can see this pin diagram. All this you can see this diagram. All these signals. So what are the input signals? These are the address lines. These are the input signals. This SOC, clock, EOC. All are. So all the signals are available here. See this clock input signal, analog input. This is the analog input voltage and ground here. So output signal. So see this output signal O0 to O7. Or you can use the in the problem they can ask that use the port A. So see this arrow and input. And input is nothing but see this. You can draw the symbols like see this. So startup conversion. You can initiate the startup conversion, and 8255 is initiate the startup conversion. Once it is done, so it can acknowledge that in the name of UOC, end of conversion. Okay, so in this one, so A port address line A, address line B, address line C. So nothing but 3:8 purpose. So address line A, address line B, address line C is given by the port B of 0, 1 and 2 signals. So this is a diagram to interface. Simply ADC, you can draw the simply ADC one side and 8255 one side. Just you just remember it is input device or output. It is input device. So the signal, the arrow is like this. You can draw the arrow is like this. Again, which port you are going to connect to this 8255 PPA? So port A, you can use this one. So then you can know that what is the SOC. What is, who can initiate the SOC? 8255 is initiate the SOC. That's why the arrow is like this. Who can given the UOC and 8280 and ADC is given the signal UOC signal. So nothing but we reference then plus 5 volts ground and analog input, and these are the output lines, and easy, very easy to remember. So PC0 and PC7 signals, the handshaking signals are stored signals. So nothing but, and which mode we are going to connect this one? Mode 1. Mode 1 we are going to connect this ADC mode 1. So because PC0, PC7, nothing but the port C signals, you can use it as a handshaking signals or some control signals. That's why only mode 1 is available, or possible mode 2 is available. So mode 1 is available for this one, or mode 2 is also available. Preferably you can connect the mode 1 to this ADC because it requires an controlling signal or handshaking signal that will be supplied by the port C signals. Okay. Okay, this is the interfacing diagram. So you must draw in the examinations also this one, this 8086 also. You not forgetting this. Remember this one. So in the diagram, they in the textbook they cannot given, but you must draw this one. This one also. Okay, this microprocessor 8086 microprocessor. Okay, so for this interfacing purpose, you require the, for this interfacing purpose, you require the some is nothing but some programming. Require some programming. Why we require programming? So 8255 only port A is working. Port A is working. So only port, so that's you write it CWR. So you can change the CWR. For changing the CWR, the only way to write the programming of 8086 microprocessor. So when you write the programming for this one, so according to the program, so it can insert the CWR register. So here our intention is, so port A is port A, use the port A is input port. Port A is an input port. Yes, because in the problem they can ask that connect the ADC to the port A. So this port A is an input port. So this is CWR. This is CWR. CWR, control over register. So in this control over register, so D7, you know that D7 bit, it is equal to 0 for suppose it is a BSR mode. It is equal to 1 input output mode. You know that very well. So you write the code is nothing but here. So a CWR register, you fill the data like this 100110000. So nothing but 98H. This is the full form of 98H. So that means port A is it work as an input port. Very easy. So how to get this 98 is very easy. So this is 0. So it must be 1 because an input output. So D5 D6 this 3 bits. You know that this remaining bits. You know that you have to remember the CWR. Once you know that CWR, so group A or group B. For suppose I can work as a group A. Group A, port A is input port. Group A. So in this group A, you can select the group A and group B by these lines. So now remaining these two lines, group A and group B, remaining two lines, port A or port B. Then see this an input port or output port simply as 0001 an input port. an input. Okay, for this one, you just how to write the microprocessor program to initialize this one. Very easy. Series move AL comma 98H. You know that why 98 initialize the 8255 PP is nothing but port A is an input port. That number, what is that number? You know that how to get that number. This is the 98. You will get this number like this. You have to remember that CWR. You have to remember that CWR. Once you remember the CWR, it is very much easy. Okay, I will show that to you that CWR. Okay. Okay, I will show that to you that CWR also. Just wait. Just wait, all of you. I will. Yes. See this. This is the CWR. You write the code for this one. You write the code for this one. So what is the code here? What is the code? In this first place, B7 bit, you indicate the one. So what is the B6 and the B7 two bits will indicate group A or group B. So I want that mode 1 or mode 0, 0, 0 or mode 1 or mode 0. So they in the example they can take the 0, 0. So nothing but mode 0, 0. These two bits. What about the remaining B4, B3, B2, B1, B0 bit? This B0 bit or D0 bit will indicate the group B bits. So we are not using at all group B bits. That's why you can put the 0, 0. Okay. So yes, that is the way you write the code for this. Okay, you understand? So this is the CWR. You fill the data whatever it. Okay, how to write this program? So 98, you know that how to initialize that 98. So that is the code of this CWR. So see this. This is 1 0 0 mode 0 mode 0. Or you can take the mode 1 also, not an worry. Take the mode 1 or mode 2 also, not an issue. But in the problem they can take the mode 0, not an issue. So 1 1 then 0 0. This total entire number 1 0 0 1 1 0 0 0 will gives the 98H. Total number meaning is 98H. So nothing but 1 0 0 1 1 0 0 0. This is 8. This is 9. So 98H. Okay, you understand how to get that 98H. So for this one, you write the program 98. Initialize that one. Now initialize means you have to send the 98H information to the CWR. That is our aim. That is our aim. So you can fill the CWR to the data 1001 1000. This is the 9. This is the 8. You fill this data to the CWR. So first of all, that's why you take that number. So you can move that number to the AL register. So nothing after that you can output nothing but out device. You can out that device. You can write that one because why you are using because you take the input device, but why you are using out nothing but you write the. So nothing but CPU series CPU 8255 to the ADC. You write the some information. You send the some information to the 8255 PPI. Nothing but to the CWR 98 data output. Then only out nothing but why you are using out device nothing but you are using input and output device. But you have the doubt that why you are but the ADC is an input device. Why you are using output device? You send the information to the output. Then so out means here out means a write instruction. In means a read instruction. Simply, you just assume that output device. So out. So then only whatever the information that is AL is stored into the CWR output device. Nothing but write. You can write. Out is nothing but the write. then 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 by this one, then 8255 PPI is now port A is input port by this converter. So you can initialize CWR as a 98H. So then after you can again take the 02H, select any of the also out of this 8 inputs of this one. You know that this is 3:8. So 8 inputs of ADC. You can select any one of the input. That may be of IP2 series. So I think in the problem also they can take the IP2. In the problem, in the input presented, they assume that an inline input is connected to IP2. So that's why. So see this. So this is the inputs, and 8 inputs are there. 8 input signals you are going to connect. Signals, 8 input signals. 8 input signals you are going to connect. So out of that 8 in the problem, they can ask that IP2. That's why take the 02 and IP2. See this 02 is the IP2 signal for selecting the IP2 signal. Because in the problem they can ask that. For suppose in the problem they can ask that 4 IP4. In the time you can load the 4. So again output port. We can write the port B and nothing but AL to the port B. AL to the port B. AL to the port B. Because now see this ports. Port B ports will work as a some series analog voltage. You can take this series. You can control this one. So port B is controlling this. So that's why you can write it and convert it. Go to AL. Then move AL00. You can clear the 00H is nothing but the startup conversion. So that again you can write the AL data to the port C. AL data to the port C. You can write the AL data to the port C. Nothing but a startup conversion. A startup conversion. Nothing but port C will work as SOC and EOC. See this. Port C is work as SOC and EOC. Port C signal will work as SOC and EOC. So, SOC means 00. Simply. SOC means 00. You can start the starting process. You load the port C as 00. Nothing but C. Move. We can just simply move the 00 to the this AL. Then this 00 to the port C. Now this is a startup. Now it starts. Okay. Now it starts. So then it takes some time to conversion. Okay, it takes. So then again move AL comma 01H, then port C comma AL. Port AL comma 01H is nothing but the port C's data, port 1 data. Then you can port it to the output. You can see this. This is one batch. See this. Change the pen. This is one instruction. You can assume this is one instruction. You can assume this is another instruction. You can see this same instruction is repeated. Move out. This is one set, second set, third set, fourth set, and fifth set also. Same instruction is move and out instruction. You can use only move and out instructions. So this is 00H can move to the port. But it can stop the so it can check this process. So once after the wait period, so conversion delay, you can send an input signal to the port. But see, this is the direction. So this ADC is send signal to the okay 8255 PPI. That's why an input you can take it as input. You can rotate. So you can see the reading of the port C as output. So J and C jump on no carry. You can see this. The carry is generated. So this is a conditional jump. conditional jump. This is the in all ports is indicates the end of conversion process. Okay, in all port A, nothing but so this is the reading of the output ports 0 to the port 7. Then you can hard start the program. Simple, very easy program. So in similar way, we can also interface the this one to the 12-bit dual slope ADC to this 85 to PPI. So this may be we are going to discuss in the next class. So